I would like to thank Dr. Kenneth Bradbury for joining us for today's session of Wisconsin Water Week as part of the Thursday Driftless Channel. Ken is Wisconsin's state geologist and the director of the Wisconsin Geological and Natural History Survey, part of UW-Madison Division of Extensions. He is a hydrogeologist who has worked and published on groundwater issues in Wisconsin since 1982, with a focus on applied problems. His research has included investigations of virus transport in groundwater flow in fractured rocks, aquitard hydrogeology, groundwater recharge process, wellhead protection, regional groundwater simulations, and the hydrogeology of glacial deposits. And with that, please give a warm virtual welcome to Ken, and he is going to take us through some of the great geology of the Driftless area. Thanks again for being here, Ken.
Well, thanks so much for inviting me today, and welcome everybody that's watching and listening. So today I'm going to talk briefly about the geology and groundwater of Wisconsin's Driftless area, which will lead up to a discussion about our SWIGG project, or Southwest Wisconsin Geology and Groundwater Project. But first I wanted to set the stage by talking about the geology a bit. But before that, I just wanted to remind everybody and who you may not know about our organization, the Wisconsin Geological and Natural History Survey. We are a part of University of Wisconsin-Madison, the Division of Extension. We're an old organization. We've been around since 1853. Our current organization dates to 1897. We are the group in the state that does research, inventory, and teaching about the rocks, minerals, water resources, and landscape of Wisconsin. And you can see some historical photos here that our geologists in the past were basically responsible for the original mapping of the geology of Wisconsin. Today we have a staff of about 28 people plus some students. Here's a picture of most of the staff on a recent field trip. But I wanted to, more importantly, direct you to our webpage, wgnhs.wisc.edu, where you can find a lot of information about Wisconsin's geology and about the projects we do. And in particular, I'll direct you to our publications tab here. And if you go there, you will find literally hundreds of maps and publications that you can download for free, both very recent and historic publications about the geology, water resources, mineral resources, and landscapes of Wisconsin. And we have recently introduced a new publications database that's connected to. So we're pretty proud of the information you can get there. So we're talking today about the Driftless area. And so the first question is, where and what is the Driftless area? Well, most people think of the Driftless area as this part of western and southwestern Wisconsin that wasn't glaciated. And on the right here is a map of the glacial deposits of Wisconsin. And you can see there's this big area in the west and southwest that looks different. And that's because it doesn't have a lot of glacial deposits of till and sand and gravel and so forth there. And on the left, just as a map of a depiction of how the glaciation looked at the end of the last glacial maximum about 18,000 years ago. We had various ice slopes coming down from the north and coming from the east, and this western part of Wisconsin is not covered. So that's the general idea of where the Driftless area is, but then more specifically, what is it really? So this is more of the scientific or geologist view of the Driftless area. Again, a close-up of southwest Wisconsin, and you can here see the rugged topography. And so the formal geologist definition of the Driftless area is the area that was never glaciated. In other words, there was never that we know of ice covering this area, and that the landscape is developed by fluvial incision of streams and rivers eroding the bedrock and making the steep hills and valleys that we see there today. And so that would be the area that's outlined by this yellow solid line. Now, the area inside the dashed yellow line, at one time or another, people have called that part of the driftless area because it has similar topography, but it's not truly driftless, because if you go to Minnesota or Iowa, you will find glacial deposits of till in some of these areas. So that's formally not the driftless area. On the right is the cover of a really great book that's edited by Eric Carson and others on our staff here, that covers the physical geography and geology of the driftless area. It's dedicated to the career of Jim Knox, who was a geography professor here, geomorphologist who passed away a few years ago and had spent his career working on the driftless area. So I'll direct you to that book, which is available from the Geological Society of America as a great resource on driftless area geography and geology. So let's begin with talking about the rocks of the driftless area. On the left, on this map is a geologic map of Wisconsin, and everything is blue. It's blue are called Paleozoic rocks, and the Paleozoic was a geological age that stretched from about 400 to 550 million years ago. And on the right is our geologic column. And most of the bedrock that you see in southern Wisconsin is of this Paleozoic age. And so the column here has many different rock units and members, and it's not important to our story today that you remember what all these are, only that there are a number of different bedrock units, different geologic formations that make up these Paleozoic rocks. And so when we look at the driftless area, we are looking at rocks of these ages from 400 to 550 million years ago. And if we start at the bottom of that section of rocks, we are in the Cambrian era. And those rocks are mostly sandstones, like you might see here at Rockbridge, at a park at Rockbridge, Wisconsin. And these are the rocks that you see in many of the outcrops in western Wisconsin. It's up here in the upper right. You can see a picture of the outcrop, and there are these ripple or cross beds in there, suggesting it was deposited by currents of wind or water. On the lower right is a microscope photograph of the sand grains, showing how well sorted and rounded and uniform they are, which makes a wonderful aquifer, by the way. And so we know that these rocks were deposited in probably a kind of a shoreline environment, and where you might have shoreline currents, a beach sort of environment, and even winds and sand dunes and cross bedding. And so the Cambrian, during the Cambrian, Wisconsin had shorelines. We had continental drift going on, of course, and Wisconsin was a different place back then. But think of that as kind of a beach environment with wind and waves and shorelines that were depositing these sands. And on the right here is a typical diagram of how these formations sit in the landscape in southwestern Wisconsin. And of course, in southwestern Wisconsin, we have uplands and we have valleys, and these formations are fairly typically forming these uplands and valleys. So in the valleys, you're going to get these sandstones, of these Cambrian sandstones, like the Mount Simon and the Tunnel City formation. As we move up to the uplands and the ridges, we have these younger units called Silurian dolomite, the Platteville galena, and the St. Peter sandstone, as I'll talk about in a minute here. And so if we look at these in the field, these are a layer cake of formations, the Platteville dolomite, St. Peter sandstone. And so this is, again, part of this Ordovician geologic section. And as we move into the upper units, there's a change. We don't have sandstones anymore. Instead, we have more limestones and dolomites. And these are things that would have formed in a shallow tropical sea, like you might find in often Florida or the Bahamas right now. And so the environment of formation here would have been shallow, again, a shallow shoreline, but more like a reef environment, like the Bahama Bank as we see here. And so those formations, which we could see if we went to an outcrop near Dickeyville, Highway 151 here, we have the Galena Formation, which is a dolomitic unit that forms many of the ridge tops. below that Decorah, which has some shale in it, and then the Platteville, which is another dolomite formation. And often that you can see these in some of these very impressive outcrops down toward Dodgeville and Platteville. And it's from the hydrogeology perspective, you will notice that there are often seepage faces along some of these units where a less permeable unit underlies a more permeable unit, and you get springs or seepage faces. Or in the winter, you can get a lot of icicles forming along there, which is a kind of a neat thing. I mentioned that there were these were formed in shallow seas, and there was life there in those shallow seas, and we can see traces of that now. We have some worm burrows here in a quarry. These are some stromatolites in a nearby quarry near Dickeyville here. So you can find fossils in these younger Ordovician rocks. We also have, as all you know, there was a history of mining in Southwest Wisconsin, and that's because millions of years after they were first formed, these rocks, when they were still deeply buried, were fractured, and then hydrothermal fluids, or fluids that hot water or hot fluids that contained a lot of minerals, were injected through those fractures and left behind deposits of galena and chalcocite and other minerals that we get lead and zinc and so forth from. And so we have a history of mining in Southwest Wisconsin. It's one of the reasons we're called the Badger State. Here's a picture of one of the mines that was present down at Scholesburg in about 30 or 40 years ago, not operating now, of course, but we need to keep in mind that there was a lot of mining that happened down there. And then, of course, we have karst formation. So karst is the landscape caused by solution and dissolution of permeable or soluble rock like limestone and dolomite. And so we have a number of features here. You see a sinkhole, and there are many small sinkholes present in Southwest Wisconsin. Here's a opening, or what geologists would call a conduit in a road cut. And then we have exposed things like caves here in different places. Some of these karst features are very, very old, and were formed literally millions of years ago, and some of them were then filled in with sediment later. Others are more recent and formed in the last few thousand years. So we have a variety of karst features. The karst features are not they're not really significant in the sense that you might get if you went to southern Indiana or Kentucky, but we do have karst features, and they're very important for understanding how groundwater could get contaminated, because karst features allow very rapid movement of water into the subsurface. So, and that's what's demonstrated here, a typical landscape with these karst features, cracks, fractures, and openings and small caves and sinkholes at the surface that allow water to rapidly infiltrate and then move through the landscape. So on the right here is a map of parts of Wisconsin where we have carbonate bedrock, that is bedrock composed of limestone or dolomite, and how deep that is below the surface. So these formations sort of wrap around southern Wisconsin, and the colors on this map indicate in the orange where they're 0 to 50 feet below the surface, and the browner color is greater than 50 feet. And as hydrogeologists, we've come to understand that in any place where carbonate rock is less than 50 feet below the surface, it tends to be a place where that rock is vulnerable to contamination. And so you can see that large parts of southwestern Wisconsin have rock like that. And so it tends to be a place where these rocks are quite vulnerable to contamination. So that leads me into the topic of groundwater. And I just wanted to give a little bit of background about groundwater. What is groundwater? It's the water that fills pores, cracks, fractures, and voids in the geologic materials between the Earth's surface. So it's water in cracks and voids. And we have a variety of different kinds of aquifers in Wisconsin that are containing groundwater. Aquifers are just geologic formations that can store or transmit usable quantities of water. And so even though, say, a granite might have some water in it, it doesn't tend to transmit very much water. And so we don't always consider those aquifers. It's important to understand where groundwater comes from. So this is a very typical diagram of the water cycle, and showing us some aquifers here, a shallow aquifer, and where it's saturated here means all the pores in that rock unit or sand unit, as it's shown here, are filled with water. So it's saturated. The top of that saturated zone is what we call the water table. So above the water table, the pores are not completely filled with water. Below that water table, they are. And the groundwater system is what's happening below that water table. And water is moving either in a long flow path from a recharge area here to a discharge area in a river or a wetland or a lake, or it could be moving to a well. And if it's moving to a well and the well is pumped, you might have a little cone of depression around that well. It's important to understand that all the water is part of this cycle, and eventually it's going to evapotranspire, go back to the atmosphere, and then land on the surface again somewhere, and it's either going to run off or become part of the groundwater system. So we have, in Wisconsin, we're lucky. We have prolific aquifers. We're a pretty humid state, as everybody knows. And we have, groundwater is pretty easy to get, but it tends to be vulnerable. And our geology determines its availability and vulnerability. And I'm going to focus now on southwestern Wisconsin. As my takeaway point here, of course, is groundwater conditions vary because of our state's geology. But that's another talk to talk about all the complexities of other parts of the state. Groundwater moves, and it's not static, it moves, and it moves in 3 dimensions. So this is a simplified map of the water table, which would be the height of groundwater, or the height of this top of this saturated zone. And you see arrows moving from high points in the landscape to lower points in the landscape. And so water moves downhill, ends up in a stream, usually. But it's important to understand that groundwater moves in 3 dimensions too. It doesn't just move laterally, but it's also moving downward under high parts of the landscape, and it can be moving upward toward low parts of the landscape, toward discharge points. And discharge points are often major features like, say, the Wisconsin River, or they can be smaller features like Black Earth Creek or a spring or even a well. These areas where groundwater, near the top of the landscape, or the top of the water table, where groundwater is going in 2 different directions, we call groundwater divides. Groundwater is moving here to the right and here to the left. And it's important to understand that these are really delineating groundwater basins, which may or may not be identical to surface water basins, because the groundwater basin doesn't necessarily have to be just the same as a surface water topographic basin. So that was a fairly simple cartoon of a system, of a groundwater flow system, but real groundwater flow systems are much more complicated. And so these are 2 diagrams that happen to be from Minnesota, but they are from parts of Minnesota that are right next to Wisconsin. So they're quite similar to what you would see in southwestern Wisconsin, where we've got this stack of Paleozoic rocks. We have some maybe karst features at the surface, and we have a water table that could be somewhat complicated depending on what formation you're in. We have bluffs, sometimes springs and seeps along the bluff. And at the bottom, you have even a more complicated picture, again from Minnesota, showing how they delineate different aquifers. The different colors here represent groundwater age, and we have young groundwater at the top and very old groundwater at the bottom, and the green are places where groundwater is mixing. And you can see that the topography of the driftless area divides this up into lots of different short flow systems. And on this side is even a more complicated, but perhaps realistic picture, again, from Minnesota DNR. And this is actually a pretty good diagram, except what I don't like about it is the vertical exaggeration, which makes this look like the Yosemite Valley, in my opinion. But we often have to exaggerate things in order to show details. So this is a little more realistic picture of what the hydrogeology of southwestern Wisconsin and southeastern Minnesota looks like, where you've got this stack of Paleozoic rocks with an eroded valleys. You have bluffs and highlands and plateaus here with these karst features, some sinkholes and cracks, water infiltrating on the surface, moving down to the water table. Some of that's moving laterally, some of it's continues to move downward, eventually to discharge to a major stream or river. But then there's also mixing with deeper groundwater. You can see some of the mixing here. And then we have wells, and the wells can be shallow or wells can be deep. And depending on their depth and construction, that may influence the water quality of that well. And I'll talk about that more in a couple of minutes. So this brings us to the SWIGG project, the Southwest Wisconsin Geology and Groundwater Project. And now that we have a little background on hydrogeology, it's an ongoing project. It's been a great project, and one thing I really like about it is it was initiated by Grant, Iowa, and Lafayette counties with funding from these counties, plus the Lafayette Ag Stewardship Alliance and a few other sources as well. The collaborators on this project are those counties, our survey, the WGNHS, the U.S. Geological Survey, the U.S. Department of Agriculture, and Clean Wisconsin. It was intended to be a 2-year project. We started it in 2018. Now with COVID, it's stretched out a little bit because there were some unavoidable delays that we had due to COVID, and people couldn't get into laboratories and so forth. But we're still in progress here. The purpose of our study is to really understand the groundwater quality of private wells in those 3 counties. And the motivation was that people have probably heard that in eastern Wisconsin, specifically Kewaunee County, there had been a lot of concern with bacteria and nitrate in groundwater, and they have karst features over there and shallow bedrock. And there had been a number of research studies done in eastern Wisconsin. So much so that the EPA got involved, and the DNR got involved, and the Wisconsin DATCAP got involved, and they created some new regulations about manure disposal and other things, which only applied in eastern Wisconsin. And there were a number of people that wanted those things to apply in southwestern Wisconsin too, but the feeling among our regulatory agencies was that there hadn't been enough research done to document the problem. And so this project, the SWIGG project, really started out as a way to document and understand what kind of problems there were in southwest Wisconsin. So our goals were to identify how widespread any groundwater contamination was. And again, we're talking of private wells here. Identify sources of contamination, and then beyond that, to analyze risk factors associated with the contamination, in other words, what's causing it to happen, and develop new geologic maps of this region of Wisconsin. The researchers are myself, Dr. Mark Borchardt, who's a research microbiologist with USDA, Joel Stoydek, who's a biologist with the USGS, and Maureen Muldoon, who's a hydrogeologist with our survey as well. And so the focus here is southwestern Wisconsin, specifically Grant, Iowa, and Lafayette counties. And again, just to remind you that we are looking mostly at these dolomite and some sandstone formations that I talked about earlier. These are the formations that most of the wells, the domestic wells in that part of the state are being developed in and served by. And as I mentioned, this is fractured rock with some karst features in it, so these wells could be pretty vulnerable. And just a little more on the geology. This is a geologic map of the bedrock in this region, and the blue crosshatch area, which is covering most of the uplands, is the Sinope group. These are dolomites, but where there are river valleys or stream valleys, the rock is eroded away, and so we get to older formations like the St. Peter sandstone or these Prairie du Chien rocks. And then way over by the Wisconsin River, the landscape is eroded down so that we can see the Cambrian sandstones there, like the Waniwak Formation. And this purple are the Maquoketa Shale, which is only present in some of the mounds, like blue mounds here. And at the very top, we have some Silurian Niagara dolomite, which is not very important in our story this morning. Now, if I know earlier in Water Week, there was a talk about the regional groundwater quality and the groundwater quality viewer that you can view online from the University of Wisconsin-Stevens Point. And that viewer they have collected water quality samples from across the state for many years, and you can look on there and find out what the general groundwater quality in any particular township or county is. And so based on that historical sampling, this is what Southwest Wisconsin and these three counties look like. This is bacteria, and you can see that based on historical sampling, we had over 25% bacteria, positive bacteria for these Grand Iowa and Lafayette counties, and that's the drinking water goal is 0. So that shows you that there was some kind of problem. But the sampling, this is based on sampling taken over many years by many different people, not done at the same time, and so it's not really a good scientific sample. It's a statistical sample, but it suggests that there was a problem there. But we wanted to go and do this in a little more organized scientific way. And what we decided to sample were these indicators: nitrate, total coliform, and E. coli. Now, nitrate is sourced from manure, human wastewater, and fertilizers. It has a maximum contaminant level of 10 parts per million. It's a conservative contaminant, meaning that it moves quite well with groundwater, and so we use it as an indicator of contamination. Also looked at total coliform as a commonly measured bacterial contaminant. Total coliform is not toxic to you, but it does indicate coliform bacteria live near the Earth's surface. They live in soil, and you don't want to find them in the well. So the drinking water goal for total coliform is 0. And the E. coli is a bacteria that's a fecal source, and so it can be pathogenic or make people sick. So it would be coming out of human or animal waste. Again, the contaminant level for drinking water standard is 0. And so finding any of these would indicate contamination of a well. In other words, you do not want to find these in your drinking water, but it doesn't tell us anything about the source of the contamination, only that it's there. But that was the first step, is looking at these things. So here's our study design. First, we wanted to determine this contamination occurrence. And so we know that in those 3 counties, there's something over 16,000 private wells. We couldn't sample all of them, so we sampled a subset, and people were enrolled randomly in this sampling. So they were given we chose them randomly, and then contacted people randomly. They were offered a chance to get their well sampled for free, and we did this at two different sampling events. The first one, we had 301 people who accepted the challenge to be sampled. The second one, we have 529 wells where the families accepted the challenge. They collected the samples themselves, dropped them off at the collection points, and then those samples were analyzed at UW-Stevens Point. And then those samples were analyzed at the UW-Stevens Point lab for bacteria, nitrate, and coliform. And we found Out of those 301, you can see the number of wells that were found. So that was the first part of the study, and I'll talk more about the results in a minute. And then we did find a number of wells that had bacteria. We then went back and resampled from the subset of wells that we knew were positive to determine the source of that bacteria. And we did that 4 times. And so we were aiming for 35 samples. We got, I guess one of the collections, we only had 34, but so there were 4 samples of 35 wells that we already knew were contaminated. These were tested for pathogens, human, porcine, and bovine fecal markers. Okay, so let's just go back to those first 2 rounds of sampling, which happened in November of 2018 and April 2019. So as I said, the first sample, we had 300 wells sampled. Those samples came back with 34% of those wells had total coliform, 4% had E. coli, and 16% had high nitrate. So when we put those together and say what percentage had either total coliform or high nitrate, and high nitrate is nitrate above the drinking water standard of 10, 42% of the wells basically don't meet drinking water standards for that sampling. This got a lot of attention. It came out right before the Governor Evers took office. It got a lot of attention in the press and a lot of interest. And I think it was one of the reasons that he declared last year the year of clean drinking water, because this seemed like an unacceptable level. We went back in 2019, sampled more wells. Interestingly enough, I think because of publicity from the first sampling, more people were interested in participating. We had a similar but slightly less detection that time. Can't really tell you why, other than things changed with time. 27% of the wells had either total coliform or high nitrate. Less than 42%, but probably still an unacceptable level. And if we look back on other statewide averages, these were generally higher than we had seen in other statewide samplings that had occurred before. So we knew that this was a problem in those 3 counties, that high nitrate and total coliform was a problem. Not a huge surprise for us, but now it's been documented in an organized and more scientific way. So again, in a way, it's told us something we thought we already knew, but it gave additional weight to that finding. So the next question is, we got this fecal coliform. Where is it coming from? What factors are involved? Oops. Well, potential fecal sources would be household septic systems, and we know there are 16,000 of those in the 3 counties. Places where septage is applied to fields, and we know that there's some of that. We're looking to find out exactly how much that's going on. It could come from hogs and pigs. We have roughly 72,000 hogs and pigs in those 3 counties, or it could come from cattle. We have 373,000 odd cattle and calves in those counties. So a lot of potential sources. Other factors could be what kind of well we are sampling. I mentioned earlier the depth of the well is important, but also how it's finished, how it's cased, how old it is might be important. How much rainfall there is, and the geology. It's interesting, I found this map that shows the cow to person ratio in Wisconsin. It's interesting to note that Lafayette County has the highest cow to person ratio of any county. In Wisconsin, 6.5 cows per person. And the other, Lafayette or Iowa and Grant have somewhat less, but a lot of cows per person down there, not surprising. The microbial source tracking is not my field, so this is what Mark and Joel worked on. So I can't really answer questions about this other than it's a very sophisticated way of looking at the water. They do this qPCR analytical method to look at these humid, bovine, and porcine specific microbes, and they do 32 microbes in all. And if you want to know how that works, you need to talk to Mark or Joel. At the same time, we've been monitoring groundwater levels. There are 3 of our long-term monitoring wells, as shown here, Grant, Iowa, and Lafayette counties, just so we can see what the groundwater was doing during our sampling period. As everybody knows, this has been a pretty wet time in Wisconsin, and groundwater levels have been reflecting that. Groundwater levels during this study have been almost at record highs, but they've been going up and down. And so this is just a hydrograph of water levels in the 3 wells, and the dashed lines represent our sampling events. And what we're trying to do with this is to look at whether the aquifer was in a recharge mode or a discharge mode at that time, but specifically, where are the recharge times when water levels are rising. Unfortunately, we didn't sample exactly at a recharge time, because you can't always predict when that's going to be. And as we're analyzing the results today, we are looking more at these recharge events to see how they correlate. So looking at the fecal sources, this was very interesting work. And so this chart is just from one sampling, the one from April 2019. And just, I know you're not going to remember all these words. I can't remember them all, but just to show you the types of things we are finding. So this again is a sample of 35 wells that we already knew had bacteria or had been positive in a previous sampling. So it wouldn't be a surprise to find something in these wells. What we want to know is what that something is. So we found that out of these 35 wells that were sampled in April, 17 of them had a bovine or cattle related microbe. 5 of them had a swine or pig related microbe. 30 of them had a human microbe. And then there were all these other non-specific microbes like cryptosporidium or rotavirus or even salmonella that could come from a variety of sources. Anything on red here is pathogenic, meaning that it can make humans sick. And so this was interesting. Now, one of the big questions that people had was, and you know, people sometimes are inclined to point fingers, and the agricultural community was saying, well, it's, you know, these things are coming from septic systems, and the non-farm community was saying, no, it's coming from, you know, feedlots and manure disposal and fertilizer. Well, we can say that these things are coming from everywhere. They're coming from animals, and they're coming from people too. So of these wells, we had 13 with a human pathogen. 32 of the 35 were fecally positive on this particular sampling. And then here's a summary of all the samplings. And again, a lot of numbers here, but it just, I won't try to go through to all of them, other than say we've got these 4 events where we went back to sample the previously known to be contaminated wells, and the percentages change some over the sampling times, but in total we've got 47% of the wells had a human pathogen, and 76% of the wells that we sampled had something fecally positive. So we know that there's a problem, and we know that we have human, we have cattle, we have pigs. All these things are getting into groundwater. So the takeaways to date, and then I'll go on to say what we're doing now. We know that there's a high percentage of wells in this 3-county region are producing water containing bacteria and nitrate above the 10 milligrams per liter standard. They frequently contain pathogens that can cause human illness, and the microbial source tracking shows that the fecal sources include humans, cows, and pigs. And now we're doing continuing work, which is going on even now, to relate these to the hydrogeologic and land use factors, which is really the hard part of this study. So, for example, there is a clayey residuum over much of the landscape called the Roundtree Formation. If you live out there, and many of you do, you've seen this. It's a reddish clayey material, and it's not very well understood. It's thought that this might be protective of groundwater below it because it's, it tends to be kind of impermeable, and yet it's not the same thickness everywhere. It's not the same character everywhere. And so Eric Carson and others of our staff are now investigating that. Here's a core they've taken, and you may have seen them out taking cores with a little drill rig like this. They're taking that out and they're developing new maps of where that material is and how thick it is. So that's going on. We're also looking at the hydrogeology of these different units. I showed this picture before, but just to reiterate that we are investigating in more detail how groundwater moves through each of these Paleozoic formations, and we're developing new maps. This is a water table map of Iowa County that we already have. We're developing similar maps for Grant and Lafayette County. From a water table map, we can determine directions of groundwater flow. These are not simple to make. It takes a significant amount of work. So we're working on that now. And then we're also looking at well construction. And why is well construction important? Well, I mentioned already that the depth of the well is going to control what part of the aquifer you're tapping, but also there's how the well is designed and cased. So the casing is the steel or metal pipe that goes down the well that you might see at the surface, but that is developed to different depths. And most older wells are cased only to a shallow depth, and that shallow depth might be only here, but the well itself, the open borehole, extends far below the water table. So here on this diagram, this would be the water table. And when you have a situation like that, contaminants up here at the land surface can move downward, get into that well, and then drop into the water table. So it's a potential contamination source. More modern wells or recent wells should and generally be cased like this, where they're cased below the water table. But we have found that in Grant County alone, there are over 900 wells that are designed like this, and most of them are older wells. But understanding, and so we're doing some statistics to see if those wells tend to be more likely contaminated than the other types of wells. And we have other things that we are looking at where we have permeable soils. Again, we looked at this round tree formation, and where do we have shallow bedrock? Depth of bedrock is often a very important parameter in looking at groundwater susceptibility. Where is the rock fractured? Karst and solution features, shallow depth of the water table, areas of rapid infiltration and recharge, which can be related to these karst features or fractures, improperly abandoned wells, wells that are orphaned or abandoned, which provide conduits, and other parameters that we're looking at, like distance to a feedlot, for example, distance to different sorts of land use fields. So our long-term challenge in the driftless area is to understand these things. And I say that these questions have been around for a while, but what should we do in the future? Maybe we will have to change well construction practices. Don't know yet. Maybe we will have to change the way we manage nutrients in agricultural landscapes. Don't know yet, but these are big questions. And we also have to think about what are appropriate long-term water quality goals for this part of Wisconsin and for all parts of Wisconsin as we try to manage these agricultural landscapes and have the goals of clean drinking water. So that's the end of my talk, and happy to take any questions if we have time, Wade.
Yeah, we have a couple minutes. Oh, sorry. Yeah, we have a couple minutes, Ken. Didn't have any questions come through, and we're wondering if the portal is if there's an issue there. But I did get a text message from my Upper Sugar River Board President asking a question. What is one of the most misunderstood aspects of groundwater contamination, and how can we work together to increase understanding?
One of the most misunderstood, well, the most misunderstood, I don't know. It depends on the. I guess depends on the context. I think one of the things I like to emphasize to people is that groundwater is a local resource in Wisconsin. It doesn't come you know, I guess a common, I don't know how, well, it's pretty common. A misunderstanding is that somehow groundwater is an underground river coming from somewhere else far away. You know, you used to hear about the river from Canada, or that it came from Hudson Bay or Lake Superior. No, groundwater is a local resource. Its local land use affects local groundwater in Wisconsin. That's maybe not as true in Western United States, but here in Wisconsin, groundwater is a local resource. And so what we do locally is affects our groundwater quality, and this gives us power. This means that we have, as people living on the landscape, we have the power to change things. If we change our land use, or we change the way we do things, we will eventually see a change in the groundwater system. That change could be slow, though, because groundwater moves slowly, and it often takes many years for changes to happen, but they do eventually happen.
All right, I think we'll have to cut it off there. I always learn a lot from Ken's talk, so I really appreciate it. We'll give him a virtual round of applause here. This will be recorded just like any of the other presentations, so if you missed something or want to go back to it, we'll have it for you in a few days, I imagine. But for now, we will end the presentation here. Thanks to everyone.
Okay, thank you.